the next topic we're going to be talking about are vector functions and space curves. That sounds very sci-fi. So what are we going to be talking about? We're going to be talking about what we call vector valued functions. Where did my laser go? Is this a laser? Yeah. Vector valued functions, some examples, and then we're going to talk also about limits and continuity about these curves. So let's get right into it. What is a vector valued function? So a vector valued function is some function that takes values in R. R here is a parameter, and then it gives me a vector, let's say in R3, it could be in R2, it could be in Rn. But it gives me vectors, so it's some parametric representation of some vectors in, say, space. So for a parameter t is going to give me something like f of t, g of t, h of t, and each one of those is a vector. Alternatively, you don't have to do all of the real numbers. Sometimes we're just parameterizing a segment of a curve. So it may be from an interval to R3 instead of just all of the real numbers. So what's happening here is that I have the real numbers. Let's say here is 0 and 1 and 2, etc. And I have space. And then each one of these numbers is being sent to some vector. So 1 is sent to some other vector here, and let's say 2 is being sent to some other vector here. And what's happening is that, so each number is sent to a vector, but you should think of the real numbers really as parameterizing time, so that we are parameterizing points in space, and if this is the point that corresponds to the 0 time, 1 time, second time, time 2, then it is moving in space, so you can think of them as vectors, or the vectors are really positions in space, and it's telling you it's parameterizing a motion in 3D space. And that motion typically will be not just a line, but it will be some curve in 3D, and this is the way we describe curves in 3 dimensions, but also how we describe complicated motion in 3 dimensions is through these vector valued functions. Okay? And then we're going to want to compute derivatives. We want tangent vectors to these motion. We want lengths of these curves. We want integrals of these curves. So we're going to do all of those calculus-y thingies for these type of functions. So, but before we do all that, I had come up with some like complicated one before, but let me just do for R of t. So R here is that function from just for any real number is going to R3, and t is being sent to 1 minus t, 2 minus 1 plus t. And they are asking me to describe the image of the function, so describe the whatever curve this is parameterizing. What do you think this looks like in space? It's a line. It's a line. Remember that you can write this. This is in vector form. So this is the parameterization in what we call a vector equation or vector form. And we can do a parametric form in that I can just write that x is 1 minus t, y is 2, and z is minus 1 plus t, which is exactly how we describe lines in space. So in this case, this is a line, and I can write this, if you want, in terms of vectors. This is 1, 2, minus 1 plus t times minus 1, 0, 1. Okay? So it's a line that passes through 1, 2, minus 1 at time 0, and then it's moving in the direction of minus 1, 0, 1 at whatever speed is given by this vector. So let me just sketch maybe in the next page. So it is 1, 2, minus 1 plus t times minus 1, 0, 1. And in 3D, what's happening is, let's see, we have 1, 2, minus 1. So this is the initial point is down here, okay? And then it's moving in the direction of minus 1, 0, 1. So it's moving in that direction. So it's actually moving in this direction. So the entire line looks like that. And then you can see, you can compute numbers. If you want values at 0, I get 1, 2, minus 1. What is happening at time 1? At time 1, I get 0, 2, 0. And then you can see that that point, I did correctly, that point is in the line. So it starts below the xy plane and then goes to the xy plane and then continues like that. And sort of in the positive x direction is moving in that direction. All right, let's do a second example. Just as a reminder of vector equations and parametric equations, let's remember that we know how to parameterize a line segment, and that is, it is a parametric equation given by a vector valued function. Do you remember how do we write such a segment? If you remember, let's sort of draw what's happening here without putting the points in the right places. Suppose I have P and Q, and I want to go from P to Q. Okay, I want to start from P at time 0 and then go to Q. So what I can do is start at P. I can start at P and then add this vector here is the vector Q minus P. So I can just go in that direction. So if I do, for example, 1 minus t times P plus t times Q, what does that do? At time 0, you can see that I get P, and at time 1, I get Q. So that is a line that is going, or a segment that at 0 is at P and at 1 is at Q. Okay, so R is going from the interval 0, 1 to R3, and at 0, I land at P, and at 1, I'm going to land at Q. Okay, so it's given by this equation. Let me just continue here. If you want to rewrite that, this is also what I was trying to do at first, is P plus T times the vector Q minus P. This is what we call the vector equation, because it's a point plus T times a vector. Okay, so I can now write that. The point P is the point 1 minus 3, 2. And the point T, and T times, and the vector Q minus P will be the difference of coordinates. So 2 minus 1 is 1. Minus 1 minus minus 3 is 3 minus 1, which is 2. And 3 minus 2 is 1. Okay, so those are vector equations, or I can write it in parametric equations that the x coordinate is given by 1 plus t, y is minus 3 plus 2t, and z is 2 plus t. You can remember this formula right here. That is a formula for a segment that goes from P to Q. And in this case, we're thinking about it as really a motion in space that is going from the point P to the point Q. This is a vector valued function. And it is the formula, the general formula for the vector valued function that gives you a segment from the point P to the point Q. And this is, either one of these is the vector equation form, and this is a parametric form of expressing the vector valued function, okay? It is a vector equation form because this is a vector, it's a point plus multiples of a vector, while this is just the parameters for that line. There was also the symmetric form for a line, but that's sort of like not the point of this section where I'm trying to put everything in terms of vector valued functions. Okay? Right. Now, what is happening here? Describe the image of the function given by cosine t, sine t, t. Now here, I'm giving this to you in two different ways. We can describe vectors in R3 in terms of the canonical vectors I, j, and k. So I can write it as a one sum of vectors, I, j, k, so multiples of I, j, and k. Or I can write it as a vector with three coordinates. But so either way, I just want you to be comfortable that we can talk about it in terms of I, j, k's, as we did, for example, when we were talking about the cross product of two vectors. But what is happening with cosine t, sine t, t? What is that parameterizing? It's a helix, yes. So how do we know that it's a helix? What you can do is, first of all, look at one cross section. You can drop it, a shadow or projection into one of the planes. And if you recognize the pattern there, that gives you an idea of what's happening in that plane, and then you can try to extend. In this case, the pattern in the xy plane gives you a hint of what's happening. So first of all, let me look at the projection onto the xy plane. In the xy plane, I get a curve. As t goes, I get a curve in the xy plane. And it is given by, let me call it, I don't know, r tilde. If I forget about the z coordinate is cosine t, sine t. What does that parameterize? A circle. That's by definition how we define cosine and sine are the coordinates of a circle as we move in counterclockwise direction. Okay? So this starts at 1 here. This is x, this is y. I start here, and I'm moving in that direction as a circle. Okay? As t goes, once I go beyond 2 pi, I'm doing circles, and I'm just like spinning around in this one circle. Okay? Now, what is happening with the z value? The z value is increasing as the angle increases. So the z value keeps track of the angle itself. So if I try to draw now what is happening in 3D, the shadow of whatever is going to happen is going to go around in circles in the xy plane. But as I start drawing, the y coordinate is increasing. So it's just going to go as a slinky, some helix, or a spiral like this, okay? But you see, it's keeping the shape, it's always above the circle of radius 1, so it's not like spiraling sort of out of control in the xy plane, it's always above this circle of radius 1 in the xy plane, but the z coordinate increases, so it is a helix like that. Now, let's try to find a vector equation that represents some curve, which is an intersection of two objects. First of all, what is x squared plus y squared equals 1 in 3D space? It is a cylinder of radius 1. Okay, so we have in the xy plane and in Let's do it a little smaller, like that. And it looks like this. It's a cylinder, okay? And then what is y plus z equals to 2? It is a plane. How can I draw y plus z equals to 2? What are some good tricks to sketch it? Y equals 2 minus z. What does that do for me? Or z equals 2 minus y. That would give me the cross section in the yz plane. That's good. So if you draw in the yz plane, that cross section of that plane will be z is 2 minus y. And that is a line that goes when y is 2, z is 0, and when y is 0, z is 2, so it's this line over here. Okay? So if you cross-section now with also if you also draw the cross-section with the cylinder looks like this. So if I continue the line like that, you can see that this plane is going to cut my cylinder like that. And it is parallel to the x. So if x can change and nothing happens, so every element in the plane that is for any x, given a y and a z, like here, then all of those points are also in the same plane. So if you go along parallel to the x plane or the x line, the x-axis, that is also in the plane. So if I just complete my drawing like that, then what I see is that the intersection is going to be something like this. Okay? So it's going to be like a circle or maybe an ellipse, depending on depending on what the angle is for the plane, the cross section will be ellipsoidal instead of circle. Okay. So what should we do? How can I parameterize this thing? What we can do is, if you see what we did here, we can do sort of the same thing. I dropped my graph, since it looks like at the xy plane, it looks like it's going to be some sort of circle. I can drop it to the xy plane, parameterize the xy plane, and then see what the z value has to be for every point in the xy plane. Okay? So I can do the same thing. And here we can see that the cross section when z is 0, or what I'm going to do is parameterize this first. So 1, parameterize x squared plus y squared equals 1. And 2, the fact that the z value is y plus z equals to 2, that tells me that z is 2 minus y. So I'm going to be able, if I have parameterized already the x and the y, then I can just give the z value. But the x and the y can be cosine t, sine t parameterizes x squared plus y squared equals 1. So if I put cosine t, sine t, and then the z value is 2 minus y, so 2 minus sine t, then this parameterizes what I want. X squared plus y squared is a circle of radius 1, and I know how to parameterize circles of radius 1. I can parameterize it with cosine t and sine t. So I know that cosine t, sine t always land in the circle of radius 1 because of the identity that you said, the cosine squared plus sine squared equals 1. But it's not just, they satisfy that equality because they parameterize the points on the circle of radius 1. Okay? So that gives me a parameterization. And notice that I parameterize that curve, And now it gives me some sort of speed and direction in which I'm traveling along the, I'm in fact starting here and going like this, okay, in circles. But that doesn't matter. In this problem, it didn't tell me at some speed or something. If it had told me that at time 0, I have to be at some point, and at time equals 100, I have to be in some other point, then I can try to change the parameter here to match that speed. But otherwise, this just parameterizes that curve in some speed that is not relevant to this problem. Let me give you one more way of looking at this again without actually doing any drawings, okay? I'm going to first write this as x squared plus y squared equals 1. And then the z value, I can solve it in terms of the other variables. So that tells me that if I parameterize the first thing, then I can parameterize the z value too. And then what I did is parameterize this as cosine t sine t. So I already have that x is cosine t, that y is sine t, and the z value is 2 minus y, but y is sine of t, so this is sine of t. And I think now your question is, why is this parameterizing what I said it parameterizes? And these two variables are going around in circles in the xy plane, and this one oscillates. The graph of this function, is 2. So if this is the value 2, and then a sine wave, but it's not the sine, it's minus sine, so it just goes like this. Okay? So the z coordinate is going up and down by 1. The amplitude of this wave is 1 because it is the sine, right? The sine values are between minus 1 and 1. So it goes as low as 1 and as high as 3. So what is happening then is that I'm going around, if this is actually the height, 2 is somewhere here, let's say. Where should I put it? If that's height 2, if the z value was constantly equal to 2, I would just go around in this way. But because of the sine, I'm going up and down. The z coordinate is oscillating between high and low. Let's try to find a vector equation that represents the intersection of this thing and that thing. Let's try to first sketch what is 4y equals x squared plus z squared. Because of the y, if it was x squared plus z squared equals 4, I could sort of parameterize a circle in the xz plane. But because of the y, this is a little bit different. But the shape itself, if you solve for y, this is a fourth of x squared plus a fourth of z squared. So it's a fourth of x squared plus z squared, which in the y direction is a paraboloid. I think somebody said over there. So this is going to look like this, a paraboloid. Okay? And it is actually, let me redo it because of the fourth, what's happening is actually it makes the paraboloid kind of wide, like that. And then y equals x is what? Y equals x is the plane like this. What do you think is the intersection of those two things? That's hard to picture. What you can do is look at the z equals 0 plane, so the xy plane, and see what the intersection is there. And what you're going to get is a line and a parabola, and you have the line and then the parabola like this. So let me actually do that. When z is equal to 0, I get y is equal x squared divided by 4, and y equals x. So this is useful sort of from the double integral point of view of if you're sketching regions. This is some parabola like this. This is a line like this. So there is going to be some intersections like that. So there is some intersection where sort of like the paraboloid is bulging out, and then it will come back in, and there will not be any more intersection, okay? But what the intersection is, it turns out that the intersection is something like this, okay? I have a better picture for you. That's what's happening. So the intersection is that sort of like ellipsoid or circle in that plane. So now the question is, how do we parameterize that thing? And algebraically, I think it makes more sense to look at it algebraically. If I do 4y is equal to x squared plus z squared and y equals x, then what's happening in the y equals x plane is when these two things are happening simultaneously. So what I get is that for x is equal to x squared plus z squared. That is what's happening in the xz plane. And then the y coordinate, I know how to get it from y equals x. Okay, so I can actually write it like this now. And if I can parameterize this thing, then the y is just equal to the x coordinate. What is this? That we learned that when you have a quadratic equation like that, we have to classify it by completing the square. So if I have 4x equals x squared plus z squared, then I can bring the x's to the other side also, and this is x squared minus 4x plus z squared equals 0. And now I complete the square. This is x squared minus 4x plus 4 minus 4, which I'm going to put in the other side of the equation as also plus 4. And now x squared minus 4x plus 4 is a perfect square. This is x minus 2 squared plus z squared is equal to 4. That's great. So the xz plane, the projection to the xz plane, it's a circle that I can parameterize and then parameterize the y coordinate. So what I want is x minus 2 to be cosine, not quite cosine because I want a circle of radius 2, right? I want a circle of radius 2, so it has to be twice cosine so that the radius is 2. So x minus 2 is going to be twice cosine. Z is going to be twice sine. And y is going to be equal to the x coordinate, which is from above, is twice plus 2 cosine t. So this is actually a parametric equation already, but in vector form, it will be 2 plus 2 cosine t, 2 sine t, 2 plus 2 cosine t. That is my vector valued equation that parameterizes. Yes.
I got a little lost on how to get the 2 cosine t.
Here, I'm parameterizing this circle. Just think of this as a new variable x prime. X prime has to be cosine and z has to be sine. But if you want to parameterize a circle of radius r, it's parameterized by r cosine t, r sine t, like in the polar coordinates, right? So we want r cosine t, r sine t. Here the radius is 2, so it's 2 cosine t, 2 sine t. So x minus 2 is 2 cosine t, and this value is the sine, but in here 2 sine t to match the radius. I'm sorry, before I answer your question, I knew I would get them wrong, and I got them wrong. This is the z coordinate, and this is the y coordinate. I got them backwards. The y coordinate is equal to the x coordinate, and the z coordinate is 2 sine t. Yes. So the question is whether you can write, when you are parameterizing something like, say, x squared plus y squared equals 1, the canonical way, which is the way cosine and sine are defined, is that you put x equals cosine, y equals sine, which matches all sort of our definitions of trigonometry. But you can parameterize circles in different ways. if you want to go in counterclockwise direction, you can do cosine t minus sine t. If you want to start, instead of at 1, 0, you want to start at 0, 1, like a clock, and go in the counterclockwise direction. Any cosine t, sine t in any combination and with any signs, any choice of signs, will parameterize the circle in different ways. It's starting at any of the 4 corners and in any of the 2 directions. You can parameterize circles. Yeah. Yeah, it will be correct because the question here is to write a vector equation that represents the curve. If they are telling me find a vector equation that at time 0 is at this point and at time 1 is at this other point, then you have to be careful how you parameterize so that you match those points. Any other questions about this problem or other parameterization problems? Okay, so we have talked very little about limits and continuity in this class, but we can do limits of vector valued functions, and the limit of a vector valued function is the limit of the coordinate functions. So if you are doing a limit, you just do the limit of the inside of the limit. And we say that a function is continuous if the limit t goes to a matches the value at a, which is the equivalent of the continuity definition for a function, except that here r is really a vector. Okay? So let me just give you one example of limits. So how would you compute the limit as t goes to 0 of this? You just bring the limit inside of each one of the coordinates. So we have to compute 3 limits of 1 plus t cubed, the limit as t goes to 0 of t e to the minus t, and the limit as t goes to 0 of sine t over t. Let's see. What is the limit of 1 plus t cubed as t goes to 0? 1. It is a continuous function, and the value of the limit matches the value of the function. If t gets to 0, this goes to 1. What is the limit of t times e to the minus t? 0. That you have to be a little bit careful just to see what's happening. If you think about it, t e to the minus t is t divided by e to the t, but it's no problem because when t goes to 0, e to the 0 is 1, so the denominator goes to 1, there is no problem there, and t goes to 0, so this goes to 0. What is the limit of sine of t over t? That is 1. That is one of those more complicated limits. There's a fairly sophisticated proof that one does when you start learning calculus, that this limit of t goes to 0 of sine of t over t is 1. Or if you are already through calculus 1, calculus 2, you can do L'Hopital's rule, except that if you use L'Hopital's rule on the internet to solve this limit, then lots of angry trolls will come at you because you prove the derivative of sine of t using this limit. So it's sort of like a circular reasoning to use L'Hopital's rule to prove this. In any case, I'm okay if you use L'Hopital's and prove that that limit is 1. So this vector function approaches 1, 0, 1 as t goes to 0.